Differential equations, lesson 3, solving differential equations, some harder examples. So we're going to have a look at a range of different differential equations. We will solve them using the separation of variables technique that you saw in the previous lesson, but the difference here will be that each of these questions will involve a slightly different integration technique as well. So they will be more complex questions than ones that just involve the simple integration processes you saw in the last lesson. So to start with, we're going to see how a differential equation and solving it may require the technique of integration by substitution. Let's have a look at an example. So here's my first example, dm by dt equals mt over 1 plus t squared. Now I can see that the rearrangement is going to have to be 1 over m dm on the left-hand side, obviously the integral of to make it legal, and on the right-hand side we will have t over 1 plus t squared dt, integral of as well. Now the left-hand side is a simple integral, so ln of mod m, and then on the right-hand side we have to integrate this result over here. So this will require integration by substitution. Hopefully you can spot that. Now I'm going to clear some space on the right-hand side for me to be able to do this. I'm going to say let u equal 1 plus t squared, du by dt is equal to 2t, and then again, not a completely legal piece of mathematics here, but we're allowed to do it for the purposes of A-level shorthand. dt equals du over 2t. Again, meaningless, which is why I put it in the quotation marks, but an allowed simplification for the purposes of A-level maths. So the right-hand side becomes the integral of t over u, and then we have du over 2t, so my t cancels on both sides and I'm left with the integral of 1 over u du and a factor of a half, which I will pull outside. So this gives me a half ln mod u plus some constant, like so, and I can finish off by writing that as a half ln of 1 plus t squared plus c. Notice I've taken the modulus sign away because 1 plus t squared has got to be greater than or equal to 1 by definition, so the modulus is no longer necessary. To finish off, I'm just going to do a little bit of simplification. So ln of mod m is equal to ln of 1 plus t squared to the power of a half, or the square root if you prefer, plus this constant, and then we will take e to the power of both sides, so we have m equals e to the ln 1 plus t squared to the half plus c, all in the power, and of course you've seen this before. We can then finally rewrite this as m equals a multiplied by ln of 1 plus t squared to the power of a half, where of course a is equal to e to the power of c, and I've split the power up previously, as you've seen previously. So here are 4 examples for you to attempt. All 4 questions involve integration by substitution once you've separated the variables. Answers will come up in a minute. Have a go at the questions first of all yourself. So question 1, first of all, we'll have a look at it up over here. So this is going to give us the integral of dn equals the integral of t square root t squared plus 1 dt, and if you want you can write a 1 in front of the dn here if it helps. So the left hand side simply integrates to n. On the right hand side we have to integrate this result over here, which we're going to do by substitution. So I'm going to say u equals t squared plus 1, du by dt equals 2t, and then this step here, which you may or may not use, but dt equals du over 2t. The integral then becomes the integral of t, I appear to have lost a dt there, t square root of u, and then du and the 2t there in the denominator. The t's cancel, and we're left with a half, which I'll pull outside the integral sign, the integral of u to the half du, which is a half u to the power of 3 over 2, then dividing by 3 over 2 is the same as multiplying by 2/3, and let's put in the plus c. This then gives me n equals 1/3 of t squared plus 1 to the power of 3 over 2 plus c. Finished. Question 2, we'll see if we can find some space to squeeze it in on the left-hand side over here. So straight away I can see that the integral is going to have to split up into 1 dy equals the integral of tan cubed t sec squared t dt. Now the left-hand side integrates simply to give me y. On the right-hand side we're going to have to use a substitution here. So my substitution is u equals tan t. Now why? Because tan differentiates to give me sec squared. So that means I can do the rearranging like that. Note the quotation marks there, because remember this is not strictly speaking a completely correct piece of mathematics, it's just a shortcut that we're allowed to use. So this then becomes the integral of u cubed sec squared t and then du over sec squared t. So this cancels and I'm left with the integral of u cubed du, which of course integrates to a quarter of u to the power of 4 plus c, and this then allows me to write y equals a quarter tan to the 4t plus c. But in this question, you will notice that we were given some initial conditions over here. Notice that t is in radians, because if we're doing any work on calculus, i.e. integration or differentiation with trig functions, we must be working in radians to be accurate. So I'm going to sub in these initial conditions. So that tells me that 1 is equal to a quarter of tan pi by 3 raised to the power of 4 plus c. This rearranges to give me a c value of -5 over 4. So my final answer, y equals a quarter tan to the power of 4t minus 5 over 4. Question 3 is an interesting one. You may have spotted that on the right-hand side, we need to factorise the x first of all, and then separate the variables. So on the left-hand side, the integral of y over y squared plus 3 dy equals the integral of x dx. So this time, the right-hand side of this is a little bit easier, as we just have to integrate x, but on the left-hand side, we have to integrate by substitution. So I will let u equal y squared plus 3. So du by dy this time is 2y, which gives me this step here, that dy is equal to du over 2y. So the left-hand side of my integral becomes the integral of y over u, and then du over 2y. The right-hand side of my integral simply becomes x squared over 2, and I'll include the constant on that side. Y cancels over here, and we're left with a half the integral of 1 over u du equals a half x squared plus c, which gives me a half ln mod u equals a half x squared plus c. Multiply both sides by 2 for simplification here. So ln mod u equals x squared, and I'm just going to call this constant c again, even though it's double the original constant there, and then u is equal to e to the x squared plus c. But of course, what is u equal to? U is y squared plus 3, so y squared plus 3 equals e to the x squared plus a constant. Now, quite often in questions you might be asked to do a little bit of further simplification. So remember that on the right-hand side we can split this up to e to the x squared multiplied by e to the c, and we can let e to the c be called a, or another constant there. So this then gives us y squared plus 3 equals ae to the x squared. And if you wanted to rewrite the whole thing in the format y equals, then this of course would be the square root of ae to the x squared subtract 3. Now our last example here, number 4. We need to separate the variables with the y terms on the left-hand side and the x terms on the right-hand side. So on the left-hand side, I am going to get sine y over 1 plus cos y dy. And on the right-hand side, I'll have the integral of 1 over 2x squared dx. Now it's the left-hand side where we're going to need to do some integration by substitution. So I'm going to need to let u equal 1 plus cos y. Du by dy is equal to negative sine y. And then dy is equal to du over negative sine y, again in the quotation marks here. So on the left-hand side, we have the integral of sine y over u and then du over negative sine y. On the right-hand side, we have, I'll take the half outside of the integral of x to the negative 2 dx. So a bit of cancellation here on the left-hand side. The left-hand side is going to very simply integrate to give me negative ln mod u. And on the right-hand side, we will get negative a half x to the negative 1 plus a constant. So let's bring back in the actual substitution for u. So we have negative ln of mod 1 plus cos y equals negative a half x to the negative 1 plus c, multiplying through by a negative here to remove the negative sign. Ln of 1 plus cos y equals a half x to the negative 1 plus c. Again, I'm not going to write minus c here, it's just another constant, it doesn't really make a huge difference. And then e to the power of both sides gives us 1 plus cos y equals e to the half x to the negative 1 plus a constant. Not the nicest of answers here. I'm going to leave it as it is here. So let's now have a look at an integral which will require us to solve a differential equation and use integration by parts after we've separated the variable. So we're going to do one example again together, and then you're going to have some questions to try yourself. So our example is that we want to solve the differential equation dy by dx equals x e to the x. So separating the variables gives us the integral of 1 dy equals the integral of x e to the x dx. Of course, the left-hand side is just y, and we have to now integrate the right-hand side, which we can see this product here is going to require integration by parts. So I'm going to say let u equal x, which gives me du by dx equal to 1. And I'm going to say let dv by dx equal e to the x, which of course gives me, when we integrate, v equals e to the x. Now my integration by parts formula tells me that the integral of u multiplied by dv by dx, all with respect to x, is equal to uv minus the integral of v du by dx with respect to x. So there's my integration by parts formula, and I've got all the components I need ready. So first of all, let's look at this bit here, the uv part. So that's this. So uv is x e to the x, take away the integral v times du by dx, which of course is these two components multiplied together. So I'm now looking at this part here. So that gives me e to the x dx. So y is equal to x e to the x minus e to the x plus c. And we have finished our example. So here are two examples for you to try yourself. In both cases, integration by parts will be required, and I've left the formula up there at the top for reference. Have a go at these yourself and then check the answers. So let's have a look at the first example. So separating the variables, we need to have 1 over y dy integrated on the left-hand side, and then on the right-hand side we need to have the integral of x sine x. And it's this product here that we can see which will require the integral by parts. So the left-hand side simply integrates to give us ln mod y, and then we have to work out the integral of this side over here. So I am going to say that u is equal to x. So du by dx is equal to 1, and then dv by dx will be equal to sine x, which integrates to give me v equals negative cos x. So I have all the component parts. Let's use the formula. So uv to start off with gives me negative x cos x minus the integral of v times du by dx, which is minus cos x dx. So on the right hand side I get minus x cos x plus sine x plus c, and that's equal to ln mod y. I can of course raise e to the power of both sides as well as needed. Example 2, separating the variables, gives me 1 over y squared dy integral of equals integral of ln x dx. So the left-hand side will simply integrate to negative y to the negative 1. On the right-hand side, I have to integrate ln x, or 1 multiplied by ln x. And you would have seen this before when you did the integration topic, how to integrate ln x by parts. So u will equal ln of x, because we can differentiate it to give us 1 over x very easily. dv by dx will equal 1, which integrates to give us v equals x. Applying the integration by parts formula, uv first of all, x ln x, take away the integral of v times du by dx, which is just 1. So this gives me x ln x minus x plus c, and on the left-hand side this is equal to minus 1 over y. If I wanted this in the format y equals, I could do a quick rearrangement like that. For example. So we're now going to have a look at some questions which involve trigonometric functions. So here's our first example, dy by dx equals 3 cos squared x. And we're given some boundary conditions in radians for this one. Separating variables, first of all, will give me the integral of 1 dy equals 3, the integral of cos squared x dx. Left-hand side very simply integrates to give me y, and the right-hand side we need to think about how to integrate cos squared x. Now, again, you may remember this from the work you did on integration previously, but you may need a reminder. We're going to make use of a trigonometric identity. If you ever have to integrate cos squared x or sine squared x, you need to make use of the appropriate identity for cos 2x, which is equivalent to 2 cos squared x minus 1, which is the format of this identity that we're going to use. If I rearrange this, this tells me that cos squared x would be equivalent to a half cos 2x plus a half. So I'm going to substitute that into the right-hand side here. So I have a half cos 2x plus a half with respect to x. So this then gives me y equals 3 over 2, the integral of cos 2x plus 1. I still haven't integrated. I might be doing more steps than you need here. I'm just trying to go for full clarity. We're now going to do the integral on the right-hand side. Cos, of course, integrates to sine, but we have this 2x here as well, which means we need to divide by that too. If you want to, you can do an integration by substitution at this point, but it's unnecessary because it's such a simple example. So really, you should know that if you have cos of kx and you're integrating it, it integrates directly to 1 over k sine kx, obviously plus a constant. So this gives us 3/4 sine 2x plus 3/2x plus a constant c. So now we need to make sure we use the boundary conditions that we were given up over here. So let's substitute those in. Y equals pi. Now we then have 3/4 sine pi plus 3/2 multiplied by the x value of pi over 2 plus c. Now sine of pi equals 0, so we can exclude that over there. So c is then simply equal to 1/4 of pi, or pi by 4. So we can write out that y equals 3/4 sine 2x plus 3/2x plus pi by 4. So now it's your turn. Have a go at solving this differential equation. dy by dx equals cos squared 2y. So I'm going to start by separating the variables. Note the right hand side this time involves cos squared 2y. So I have the integral of 1 over cos squared 2y dy equals the integral of 1 dx. The left-hand side I'm going to rewrite as sec squared 2y dy. The right-hand side simply integrates to x and will include the constant on the right-hand side. Now, you should know that tan x differentiates to sec squared x, so sec squared will integrate back to tan. But of course, there's this factor of 2 here, so it will integrate to give us a half tan 2y equals x plus c, and I will leave the answer in that format there. If you wanted to, you could rearrange. I'm not sure there's a huge amount of value in doing that unless you're asked to do that. If you wanted to, you could say that tan 2y equals 2x plus a constant. Again, you can just write it as a plus c, doesn't really matter too much. 2y is then equal to arctan, or tan to the minus 1 of 2x plus a constant, and then y equals a half tan to the minus 1 2x plus c, or some constant. So we're now going to look at differential equations which require knowledge of partial fractions before you can actually carry out the integration. Now, the example I've chosen, I picked because I've seen people make a lot of mistakes by trying to add h squared to both sides to separate the variables. We saw a similar example but without the square feature previously, and you need to make sure you think of this 400 take away h squared as a single entity. So I'm going to leave the 200 on the left hand side like that. So we have 200, the integral of 1 over 400 minus h squared dh, and on the right hand side we have the integral of dt, like so. Now on the left hand side we need to remember that this denominator is a difference of two squares, so it can be factorised as 200 minus h, 200 plus h dh, and the right hand side simply integrates to give us t. So before we can integrate the left hand side, we are going to need to deal with this. So 1 over 200 minus h, 200 plus h. We're going to need to write it in the form of a partial fraction decomposition. So a over 200 minus h plus b over 200 plus h. Now, this tells me 1 is equivalent to a multiplied by 200 plus h plus b multiplied by 200 minus h. Imagine you're multiplying all three terms by the denominator of the red fraction on the left, and you will get this result here. Now, some people like to compare coefficients, some people like to use a substituted value. I'm going to substitute in sensible values here. So if h is equal to negative 200, this gives me 1 is equal to 400b, and therefore b equals 1 over 400. And then if h is equal to positive 200, again subbing into this result here, this gives me 1 is equal to 400a, so a is equal to 1 over 400. So this then tells me that my integral, in a minute, we'll come to that in a second, my partial fraction decomposition is 1 over 400, 200 minus h, plus 1 over 400, 200 plus h, subbing in my values of a and b. So, integrating these, well, remember we also have a factor of 200, which will simplify with these factors over here. So they will become factors of a half. So we now have a half the integral of 1 over 200 minus h dh plus a half the integral of 1 over 200 plus h dh equals t. Make sure you can see what I've done here. I've replaced this single fraction with these two fractions here, but I've made sure to multiply both of them by 200, and I've split them up into two separate integrals as well. So, thinking about the integration, we know these are reciprocal functions. They will integrate to natural log functions. So we have negative a half ln mod 200 minus h plus a half ln mod 200 plus h equals t. Now we do need to include a constant at some point. I think I'll include it on the right hand side here, so t plus c. Now we have a simplification we can do on the left hand side in that we have one natural log take away another natural log. So I can write this as a half ln mod 200 plus h, subtract ln mod 200 minus h, and that's equal to t plus c. And the last step is to combine the logs on the left hand side, so we have ln mod 200 plus h over 200 minus h equals t plus c, and that's going to be our final answer. So now it's your turn. There are two questions here for you to have a look at, both involving partial fractions. You may want to watch the video through as you do the example. You may want to try the example yourself first of all, and then check your answer or seek guidance with the video as you need it. So question 1, let's take a look at that first of all. So I'm going to separate my variables first of all. W terms need to be on the left hand side, so you can see they're clearly both going to be in the denominator, which is going to be the product of these brackets here. So the left hand side looks like this, the right hand side looks like this. Now the right hand side is obviously going to integrate very easily to give me negative a half t, but what I have to do is apply a partial fraction decomposition to the left hand side over here. So let's say 1 over w minus 4 w plus 5 is equivalent to a over w minus 4 plus b over w plus 5. This then simplifies to give us this result here if we either give all the terms a common denominator and then look at the numerators, or simply multiply all three terms through by w minus 4 and w plus 5 to get to this line here. Now, I'm going to substitute in values which will result in the brackets becoming 0. So if w equals negative 5 first of all, that gives me 1 equals negative 9b, so b equals negative 1/9. If w equals 4, this then gives me 1 equals 9a, so very nicely a then equals 1/9. So my partial fraction decomposition here is 1 over 9 w minus 4 minus 1 over 9 w plus 5, like that. And I have to integrate these two results up over here. I'm going to take the 1/9 outside of the integrals, so 1 over w minus 4 minus 1 over w plus 5. You can either do these as two separate integrals, or the integral of the subtraction here doesn't make any difference, and this is equal to negative a half t on the right hand side. So let's integrate each of these separately. So we have 1/9 ln mod w take away 4 take away ln mod w plus 5, and I'll keep the factor of a ninth outside like that, and this is equal to negative a half of t plus a constant as well. Now we might want to rearrange this in some particular way. We may not have been given that information, but you are likely in an exam question to be directed to a particular form of rearrangement. I'm going to multiply both sides by 9, so I have ln, and on the left hand side I'll combine my logarithms like this, and on the right hand side I've got negative 9 over 2t plus a constant. Again, it'll be 9 times the value of the previous constant, but it's still a constant. So e to the power of both sides gives me w over 4 over w plus 5 equals e to the negative 9 over 2 plus constant, and of course we might want to write this as ae to the negative 9 over 2t, again using the techniques that we've seen in previous lessons about how we split up the e function. Right, question 2, let's take a look at our integral here. So separating the variables, y terms on the left, we have y minus 3 over y bracket y minus 1, integral of with respect to y, equals the integral of x dx on the right hand side. So we have to take y minus 3 over y bracket y minus 1 and decompose it into its partial fractions, like this. So we end up with this result here, with no denominators in place. Now choose your y values carefully. Y equals 1. This gives us negative 2 equals b straight away. And then y equals 0 gives me negative 3 equals a. So I have my two values. So the decomposition looks like this. Negative 3 over y minus 2 over y minus 1, like so. So we now have to integrate this on the left-hand side. So this gives us the integral of negative 3, 1 over y dy, minus 2, the integral of 1 over y minus 1 dy. I could have left it as one single integral. It doesn't really make a huge amount of difference. And on the right hand side, that x is simply going to integrate to a half x squared plus a constant. So on the left hand side, I have minus 3 ln mod y minus 2 ln mod y subtract 1 equals a half x squared plus c. Now again, you may wish to combine, simplify, use logarithms or laws of logarithms. There are different things that we can do here. I'm going to leave the answer like this for the moment. Now we're going to finish off by looking at 3 slightly different examples which don't necessarily fall into any of the previous categories, but which are all interesting and slightly different in their own regard. So example 1, the differential equation we are going to solve is dh by dt equals the square root of h over 1 plus h all squared. So h terms are going to have to go on the left when we separate variables, so we'll end up with the integral of 1 plus h all squared over square root h with respect to h equals the integral of dt on the right hand side. Now, quite often I see students getting to this point and then deciding they are stuck and that they can't do anything further, but think about what you could do. 1 plus h all squared can be expanded to give you 1 plus 2h plus h squared. Now, 1 plus h all squared over the root of h, or h to the power of a half, then simply means you have these 3 terms all to be divided by h to the half. So each term divided by h to the half gives you a single term, h to the negative a half, plus 2h to the half plus h to the 3 over 2. This means that the integral on the left-hand side simply becomes the integral of these three terms, and it's actually a surprisingly easy question. The right-hand side simply integrates to t plus a constant. So what does this give us? This gives us h to the power of a half multiplied by a factor of 2, 2h to the power of 3 over 2. Now dividing by 3 over 2 is the same as multiplying by 2/3, so we end up with 4/3. And then we have h to the power of 5 over 2, and again dividing by 5 over 2 is the same as multiplying by 2/5 equals t plus c. So it's this step over here that people can quite easily get to, but it's remembering that this actually becomes a very simple integral afterwards that's quite crucial. So question 2 is another one where I've seen people quite often not know how to start. Remember your laws of exponentials. The right hand side could be split up like this: e to the 2x multiplied by e to the minus y, or if you wanted, dy by dx equals e to the 2x divided by e to the y. Think about your laws of indices. Now you've got two separate terms in x and in y, so we can separate the variables. So we end up with the integral of e to the y dy equals the integral of e to the 2x dx. Left-hand side simply integrates with respect to y to give us e to the y. The right-hand side simplifies to give me a half e to the 2x plus a constant, like so, and then we can take natural logs of both sides, which gives me y equals ln of a half e to the 2x plus c. There isn't really any useful further simplification that we can do here. Now here's one final example, again where I see people sometimes feeling a bit confused and not knowing where to start. Always look at something like a square root and see if you could think about another way of writing it. I am going to write it like that. So both parts of the fraction are raised to the power of a half. Then let's separate the variables. So on the left-hand side, we will have 1 over y to the half dy being integrated. And on the right-hand side, 1 over x plus 3 to the power of a half being integrated with respect to x. It's often a lot nicer to rewrite these as negative powers. Makes it a little bit easier to apply the integration. The left-hand side, we simply get 2y to the power of a half. The right-hand side, you can use integration by substitution, but it's such a basic result here that it's a linear function, x plus 3 being raised to a power. So raise the power by 1, divide by the new power is a half, dividing by a half gives you a factor of 2, and then plus c at the end here. It's important in these differential equation questions to get as much practice as possible, and remember that you could be asked to apply any of the various integration techniques: substitution, parts, using trigonometric identities, using partial fractions, using standard integration year 1 techniques as well when you're solving a differential equation. Again, as with many aspects of maths, practice is crucial here. In the next lesson, you'll be looking at solving a wider range of problems, including word-based problems you may have to form and then solve the differential equation, and we'll be scaling this up to the most complex sorts of examples.